All right, so let's study this system. And this differential equation, you can actually solve explicitly because it is separable. So you could solve it explicitly, but that's not what I want to do. I want to study it just by studying the differential equation and studying, sort of thinking about on the phase line, what this law for growth of infection is going to be saying. So let me draw a phase line here. So when I say this is a phase line, I mean this is like my x-axis, and different points on this line represent different numbers of infected people. So somewhere there's 0, and anything to the left of 0 doesn't make sense. It's not even included. In fact, let me just delete this arrow here. Everything starts at 0, since you can't have negative number of infections, right? So these different points on this phase line represent different levels of infection. Now, the differential equation has different things to say about different points on the phase line. And by the way, this is autonomous. This differential equation is autonomous because you can see there's no explicit time dependence on the right-hand side. There's no t's showing up. So that means when I focus on any particular point on the phase line, if that happens to be the current state of my system, then the differential equation tells me exactly how the state will change from there. Okay, so I'm actually going to introduce a vertical axis, but only temporarily, to help think about what the differential equation says about different points on the phase line. So I'm going to introduce a vertical axis here, and it will be the axis that shows me what is dx dt. And after I'm done getting the information I need from this second axis, then I'm going to erase it and get rid of it, and I'll have a nice phase diagram at the end. So the reason I'm doing this is because I want to examine, the differential equation says something about each point here in the phase line, right? For each point, the differential equation says, okay, if you're there, if that's what x is, then this amount is what dx dt will be. So each point here has a dx dt associated to it. So I'd like to plot what are those various dx dt's. Okay, well, there's no way I can plot this, considering that there are these unknowns r and alpha. There's no way I can plot this exactly. But I just want sort of a qualitative plot that tells me what's going on. And perhaps it can tell me what's going on in terms of r and alpha, even though they're unknown. What I do know is that r is greater than 0 and alpha is greater than 0. So that is important. Okay, well, if I were to plot, so what I'm doing is just plotting a function of x, right? X is now the horizontal axis, and I'm plotting this function of x, which is dx dt. As a function of x, this is just a parabola, right? It's a quadratic function of x. And since the coefficient in front of x squared is negative, minus alpha is negative, it's going to be an upside down parabola of some kind. So something like this maybe, or like this. Who knows what the parabola exactly looks like, but it's an upside down parabola. Okay, well, if I want to draw an upside down parabola and I want to draw the correct one, then one thing I can do is figure out where the parabola will cross the axis, where it will cross 0. So where is dx dt equal to 0? So let me solve. So this is the question. For what x is dx dt equal to 0? And to answer that, for an autonomous differential equation, there will be just an equation involving x that answers that. So the question is just, for what x is rx minus alpha x squared equal to 0? And, if this were a more complicated quadratic polynomial here, then I might use the quadratic formula and find the two places where it crosses. But it's quite simple because you can just pull out an x. Right? So what are the solutions to this equation? X equals 0. And another solution is, so if I look at the equation r minus alpha x equals 0, that would be, solve that. That would be x equals r over alpha. So there are two important locations. You could say there are two critical locations on this phase line. One of them is here, at x equals 0, and one of them is, I don't know exactly where to draw it, but r over alpha is some positive number, so let me just draw it somewhere. There. So there is r over alpha. And if I want to plot dx dt as x varies, it's going to be a parabola that is an upside down parabola, so it's cupped that way because of the negative alpha in front of the x squared here, and it crosses these two yellow dots. Okay, so now I'm starting to get a better idea as to what's going on. These two yellow points, these are called critical points. So these 2 points that I solved for here, these are critical points. And usually they're denoted by x star. So these are two possible values for x star. That's just the notation used in your textbook, so I'm just following it. And it is kind of a common notation for critical points, x star. So there are two x stars, 0 and r over alpha. So actually, let me go ahead and officially define that term critical point. Given an autonomous differential equation, like x prime equals, let's say, let me use f of x a critical point is a point x star satisfying x of t equals satisfying f of x star equals 0. So the critical points of an autonomous differential equation are just the zeros of the right-hand side function. So they're just the zeros of f. They're where f equals 0. And the significance of these is that when x star is a critical point, you get an equilibrium solution. So then x of t equals x star becomes an equilibrium solution. Equilibrium just means constant. So here x star is a constant, and I'm saying x of t equals x star for all t. X is not changing in time. So the way to be convinced of that, or to see that that's true, is plug in your critical point as a constant function into the differential equation. What's the left-hand side? And what's the right-hand side? And do they agree? So on the left side, the derivative of this constant, x star, is going to be 0. And on the right-hand side, f of x star is going to be 0 because x star is a critical point. That's what critical point means. So they agree, and it's a solution to the differential equation. So you get these equilibrium solutions. Equilibrium just meaning they don't change in time. And so back here, these 0 and r over alpha, these are equilibrium solutions actually. If the number of infected people starts at 0, then it will remain 0 forever. That makes sense. That's an equilibrium solution. Everything's in equilibrium if there are 0 infected people. On the other hand, if there are r over alpha infected people, then sorry, not on the other hand, on the same hand, also if there are r over alpha infected people, then apparently that will also be a situation where the number of infected people does not change in time. So if you plug in x equals r over alpha, you get 0 on the right side and 0 on the left side. Okay, so that tells us about 2 solutions to this differential equation, but there are also many more, right? So this tells us about the solutions where the initial conditions are 0 or r over alpha. So if your dot starts at 0, then it'll stay there forever. If your dot starts at r over alpha, then it'll stay there forever. On the other hand, if the dot starts anywhere else, then it will move, because dx dt will not be 0. So another useful thing that the critical points will do is, since they're telling you where dx dt is going to be forced to vanish, they're also dividing the phase line into subregions, where in some of those subregions, like this is one of the regions, this is another region, where in each subregion the derivative takes on one sign. It's either positive or negative. And the reason for that, of course, is that if the derivative function is continuous, then if this function here is continuous, then in order to change sign, it has to pass through 0. So you have to get a critical point. So just from the picture, from what we've pictured so far, we can see that in this region, we have the derivative dx dt is positive. And in this region, dx dt is negative. And in that region, it's also negative, but that region doesn't make any sense. It's not part of our phase line. Okay, so that tells you what's going to happen to the number of infected people. If the number of infected people is, let's say, is anywhere in this region, then the number of infected people will increase. So if there's this many infected people, then the number of infected people will increase. If the dot starts here, it will move to the right. On the other hand, if there's this many infected people, then the number will decrease. Okay, that doesn't make any sense. So that should have surprised you right there. The number of infected people can decrease? Hang on, we did not build recovery into our model. People can become infected, and infected people can infect more people, but we never built recovery into the model. Maybe we could do that later, and that would give us a better model, but how can the number of infected people decrease? Well, just look at this. It becomes negative if x is large enough, right? Well, I guess the model breaks down at that point. When x is so large that, so if you keep increasing x, then eventually you reach this point where dx dt is 0. You can no longer get any new infected people. Given the diagrams with the white dots and the red dots that we were drawing in the last video, what must have happened if we reached that state? If we reached this yellow dot where the number of infected people is just no longer increasing? That must be the situation where everyone is infected. That's a situation where there are no more infected people. So once everyone is infected, the infection rate should be 0, and that makes sense. But what if you set x to be higher than that? Then you would be saying that there are more infected people than there are people. That doesn't make sense. So the model breaks down once x gets bigger than r over alpha. And it breaks down because it seems, based on the fact that we have a yellow dot here at r over alpha, it seems that when you set things up with the proportionality constants like this, it seems that r over alpha must be the number of people that your model is assuming there are, the total number of people that there are to infect. So we should actually cap off our phase line right there. Now, there are other uses for a differential equation like this, not just for a model that tells you about the number of infected people during an epidemic. It can also tell you about population growth under situations where there's environmental limitations or competition among organisms for limited resources in the environment. In those situations, it makes sense to use a very similar model, the same model as this, and in those situations, this R over alpha is not going to represent the total population, so it might actually make sense to have more of a population than this number. So this will not always happen anytime you consider this model. That's just happening here in this situation. So anyway, the information we can get out of the phase diagram here then is basically what you're seeing here is if the number of infected starts here, it stays the same. If it starts here, then it stays the same. And these represent no one is infected and everyone is infected. And if if the number of infected is very close to 0, then dx dt is going to be not so large, right? This is not so high. So maybe we could represent that by putting a small little arrow there. On the other hand, if the number of infected people is like in the middle between 0 and full, then dx dt is quite large. So let's make this a big arrow. And if the number of infected people is close to everyone, then again, its dx dt is quite small. So the overall phase diagram wouldn't have so much clutter. It would just show you sort of this part. So let me show you. So it would look just something like this. And this sort of has all the information. These dots are critical points, and it's telling you if x is any particular value along here, what's going to happen to it. If it's here, it's going to increase, but slowly. If it's here, it's going to increase quickly. If it's here, it's going to increase slowly. And if you allow the differential equation to continue playing out in regions where it doesn't necessarily make sense, interpreting x as the number of infected people, then you get more information. So like back here, if you go to the right here, then this blue line goes below the axis, dx dt becomes negative, right? And also if you go to the left here, dx dt becomes negative. So a more complete picture would be something like this. So here, if x is bigger than r over alpha, then it begins to decrease, slowly at first. If x is much bigger, then it decreases very quickly. If x is very negative, if x is a little negative, it decreases slowly. If x is very negative, it becomes more negative quickly. So this kind of shows you if x starts at a particular place, what it's going to do. Now, the critical points, so we observed that the critical points give you equilibrium solutions. But there are different kinds of equilibrium solutions. So here, this kind of picture, this would be called a stable equilibrium. And this picture here is an unstable equilibrium. The difference being, with a stable equilibrium, so they're both equilibria. So if your initial condition is 0, you will stay at 0 forever. If your initial condition is r over alpha, you will stay at r over alpha forever. But the difference is that if you start at 0 and you change a little bit away from 0, so make a slight perturbation to your initial condition from 0, then you will actually run away from 0. So if you start at a very small positive number, very close to 0 but not quite 0, then you will run off to the right. And if you start with a very small negative number, just a little to the left of 0, it'll run off to the left as time goes on. So you would say 0 is an unstable equilibrium. You really have to be exactly at 0 in order for you to remain at 0 forever. So the running off to the right represents if you had just a little little tiny part of the population gets an infection, maybe just one person becomes infected, then the number of infected people runs off to the right here. Stable, on the other hand, if you perturb in either direction from this equilibrium, then you tend to go back towards the equilibrium. So the main thing I want you to take away from this is that we were able to analyze what happens with this differential equation without actually solving it. So we never solved the differential equation here. You can solve it, you can separate variables and integrate, but we didn't have to figure out what it's saying will happen to what it's saying will happen in the long term. So you can tell just from this phase diagram, so this is a phase diagram, you can tell just from this, without solving the differential equation, that if your initial condition is here, then in the long run you're just going to approach r over alpha. And if your initial condition is here, in the long run you're just going to approach r over alpha. And if your initial condition is here, then in the long run you're just going to go off towards negative infinity. So you can tell these things without actually solving the differential equation. This is incredibly useful because it is often hard to solve differential equations. So it's incredibly useful to be able to get information out of them even without solving.